Great, thank you. Thank you very much. So it's a great honor for me to be speaking at this conference for Elaine's 70th birthday, especially because she has been like a great inspiration in my life. Mathematically, her work is fundamental and awe-inspiring, and it seems no matter where I go, whether it's vanishing theorems in commutative algebra or K-theory or the subject of the talk today, Elaine's been there first. And I suspect I'm far from the only person that feels this way. And at a personal level, it's been a great joy to get to know her over the last 10 years, first as a mentor and also, dare I say, as a friend. And it's been just wonderful. So I look forward to many more years of friendship in mathematics. Okay, let me now get to the business. So share my screen. Hopefully this works. Can people see the screen?
Yes.
Okay, great, thank you. Right, so the subject is local systems and Higgs bundles in p-adic geometry. Everything I'm describing is joint work in progress with Mingjia Zhang. And so the story begins with the classical non-abelian Hodge theory over the complex numbers. Due to the work of a lot of people, but especially Corlette and Simpson, we understand that if you're working with, let's say, smooth projective varieties over the complex numbers, you can relate local systems on the variety to Higgs bundles on the variety. And this is very interesting and useful because local systems is a transcendental invariant, whereas Higgs bundles is a purely algebraic invariant. And so the goal of my talk is to explain an analogous picture in the p-adic world. I'll get more into it in a second. But it turns out that maybe better if you want to go from the complex world to the p-adic world, in this case, it's better to make a detour through characteristic P. And so first, actually, let me tell you about non-abelian Hodge theory over FP. Because whatever structures we see in non-abelian Hodge theory and characteristic P are going to have exact analogs in the p-adic setting. And so let me remind you first what the picture looks like in the simplest case. And so everything I'm describing here, I think, goes back to work of Bezrukavnikov, Ogus Vologodsky, and perhaps several other people. I want to ignore some twists, so let me just simplify life and work over FP itself. So let's say X over FP is a smooth variety. So the central object in non-abelian Hodge theory over FP is D modules. So dx is going to be the sheaf of differential operators on X. So these are differential operators in the sort of crystalline sense. So for affine space, I'm talking about the Weyl algebra. And so modules over this are called D modules, and we would like to understand them better. And it turns out that there is a very sort of fairly simple algebraic way of getting at them, which is based on the following pair of observations. Or results. So the first result is something about the center of the ring of differential operators. So the center, Z stands for center, turns out to be very large in characteristic P. So an easy way to see this is first you observe that functions, if you have any function on the variety, well, a function does not commute with a differential operator, but the pth power does. And so already functions to the pth power sit inside the center. Turns out you can do something similar for derivations. And in fact, the center is canonically identified with the symmetric algebra on the tangent bundle of X. And again, I'm suppressing some push forwards. You should probably be decorating this with certain push forwards, either from along Frobenius or from the tangent bundle downstairs. Let me just ignore them because it will just be confusing. And so the center is pretty large. It's the symmetric algebra on the tangent bundle, and it's via the so-called p-curvature construction. Oops. Psi. And so the p-curvature map is given by sending functions to the pth power. And more interestingly, if I give you a derivation, you can look at its pth power as a differential operator and subtract off its pth power as a vector field. So you remember the fact that the pth powers of vector fields in characteristic P are vector fields. And so the center is very large. This is very different from what happens in characteristic zero. Um, and moreover, it's so large that the sheaf of differential operators is actually pretty close to the center. More precisely, it's an Azumaya algebra over the center. The rank of the Azumaya algebra is like p to the dimension of x. And so why is this useful? It's useful because it means we can reorganize the theory of D modules in terms of a very much more linear looking object. So let me state it like this. So recall that Azumaya algebras over a scheme correspond to Brouwer classes or certain Brouwer classes. I want to think about them geometrically. So I want to think about them as GM gerbes. And so one way to rewrite this is the following. So there exists a GM gerbe P of x over the cotangent bundle. So the algebra of functions on the cotangent bundle is the symmetric algebra on the tangent bundle. That's why the gerbe lives over the cotangent bundle. And this GM gerbe has the following sort of key property. So plus an equivalence between the category of D modules on X and the category of quasi-coherent sheaves on T star X twisted by this gerbe. Or another way to write it is just as sheaves on the gerbe. So let me write it like that. So sheaves, quasi-coherent sheaves on P of X, which have degree 1. And so what does this mean? Whenever you have a GM gerbe, that means that this P of X has an action of BGM, the classifying stack of GM, and the quotient by the action is the cotangent bundle. Whenever you have a stack which has an action of BGM, its category of quasi-coherent sheaves has a natural Z grading. Essentially, if you look at a point, at every point of the stack, you have a representation of GM, you break it up into its eigenspaces, and that gives you a sort of global Z grading. And the degree 1 part of that category corresponds to D modules. And this is going from the statement that D is Azumaya over the center to the statement about a gerbe is just some general statement about Azumaya algebras. And so now we've realized D modules in terms of things that look much more linear, coherent sheaves on some auxiliary geometric object. And maybe you don't care about all D modules, maybe you only care about a certain subcategory. And so let me isolate that subcategory. So inside here, we have the subcategory of vector bundles with flat connection, which is the kind of thing one is usually interested in when one talks about de Rham local systems. And then inside here, what does that correspond to? It essentially corresponds to Higgs bundles. So I will call it p-twisted Higgs bundles. And then I'll say what that means. And so what this means is concretely, you look at those coherent sheaves on this gerbe, which have degree 1. Oops. Sorry. And they satisfy 2 conditions. So the first condition is that the support of E is finite over X. And the second condition is that E is locally free over its support, or flat over its support, flat over X. And so let me just draw a picture to explain what's going on here. Here's T star X. Here's a projection to X. If you have one of these sheaves E, by assumption, it has some support which is finite over X. So the support looks something like this. This is the support of E. And E can be thought of as a coherent sheaf on this finite cover of X. And the assumption is that when you push it down to X, it's actually flat. So if you haven't seen this before, it's a pleasant exercise to just make sure that when there is no twist, meaning if the gerbe was actually trivial, then this is exactly the category of Higgs bundles. And so now we have a slightly twisted version of the category of Higgs bundles, which turns out to be equivalent to the category of D modules. And so this is the picture to keep in mind that we want to mimic later. Okay. So this is one fact. It realizes D modules in terms of twisted notion of Higgs bundles. Now you might wonder if you can go further and get rid of the twist. It turns out you cannot in complete generality. So in fact, it turns out that D is never trivial as an Azumaya algebra in the Brouwer group of T star X. Well, okay, Ofer is not in the audience, but as long as the dimension of X is bigger than 0. He's here, thankfully.
Is a p-twisted Higgs bundle just a usual sheaf with an action of the Azumaya algebra structure? Is that?
Yes, that's how this. Yeah, exactly. That's how this relationship between sheaves on an Azumaya algebra and sheaves on the gerbe goes. Sort of modules over the Azumaya algebra are the degree 1 part of the corresponding category, and the other degree parts correspond to modules over tensor powers of the Azumaya algebra. Right, so D is non-trivial, and so you can't quite get a statement with all Higgs bundles on the nose, but maybe you don't care about all flat vector bundles, but only some subcategory of them. And so Ogus and Vologodsky figured out that even though the gerbe is non-trivial on the entire space, on certain loci inside the cotangent bundle, you can trivialize the gerbe. And then once you choose such trivializations, you'll get an honest equivalence with Higgs bundles. And so let me just write one statement that they proved. So if X is lifted to Z mod P squared, so if you choose a lift mod P squared, you can trivialize the gerbe over a certain infinitesimal neighborhood of the 0 section. So over the pth infinitesimal neighborhood of the 0 section. So let me write 0 of X for the 0 section. In fact, you can do better. They prove really that there is a sort of PD neighborhood of the 0 section where this can be trivialized. But let's just focus on this statement. And so what this means is that if you restrict this equivalence to those sheaves which are supported in this neighborhood, then you can ignore the twist. And so if you go through what that tells you, you get the following statement. So you look at vector bundles with flat connection on X, whose p curvature is nilpotent of order less than or equal to p minus 1. That corresponds to being supported on this neighborhood. And those are equivalent to the same kinds of Higgs bundles. So if you constrain the order of nilpotence of the p curvature, you get a correspondence similar to what you see in characteristic 0. And it's very useful for various applications because nilpotence of the Higgs field is, for example, is true for local systems that would come from geometry. So the goal of this talk is essentially to describe a p-adic analog of this story. So we want some analog of 1 and some analog of 2. And it turns out that it works out quite nicely. One thing I want to emphasize maybe before I go on is that in the complex story, it was really important that X was compact. This was not the Corlette Simpson correspondence is not a local statement, it's a global statement. In the characteristic P story, it's a local statement. I didn't assume any properness. All these statements are correct. And the same thing is going to happen in the p-adic world as well. Okay, so that's my cue to segue into the p-adic world. Are there any questions before I start doing that?
Sorry, then send me to check. So your equivalence is also symmetric monoidal, right?
So that's a good question. I was going to try to avoid this. So this equivalence is symmetric monoidal, provided you're careful about what symmetric monoidal structure you use here. The standard symmetric monoidal structure on quasi-coherent sheaves is going to move the gradings around. Two things of degree 1 tensor together to give you something of degree 2. So that's not what you want to use. What you need to observe is that the cotangent bundle is actually a group. So it has a group structure. And it turns out you can lift this group structure canonically to a group structure on P of X. And so P of X has another, it has a group structure. And so the quasi-coherent sheaves on it has another symmetric monoidal structure given by convolution. And if you use that symmetric monoidal structure, then this is symmetric monoidal equivalence. Thank you. This equivalence cannot be symmetric monoidal just because the categories aren't stable under taking tensor products. You can't, if you tensor enough times, you lose the nilpotence condition. Other questions? All right, so if not, let me talk about the p-adic story. So the story, as far as I understand, begins around 20 years ago in the work of Faltings and also Deininger-Werner. And there's been a lot of work since then on this question. A beautiful result was obtained last year by Ben Hoyer, which I'll recall when I get to it later. And certainly everything I'm describing was motivated by what happens there. But I'm not going to be able to do justice to all the work that has happened here. So I apologize if I don't talk about your theorem. So the setup is going to be the following. So C is a perfectoid field. You can just take it to be the p-adic complex numbers if you wish. And X over C is a smooth rigid variety. So even if your ultimate interest is algebraic geometry, at some point in the discussion, it will be crucial to switch to thinking about things in terms of rigid analytic spaces. So let me stay in that setting right from the start. So the first thing I need to tell you is what the analog of D modules is, or what is the category that we're trying to describe in terms of Higgs bundles. And so this was already in the original work of Faltings. So who found that there's this enlargement of the category of local systems, which has a much more coherent flavor. So let's say you're interested in complex local systems on X. And I mean, in the étale topology with the usual caveats that you have to do some limit procedure. If you want to say it correctly and simply, you just say it's complex local systems in the pro-étale topology in the sense of Schulze. Any definition will work. And this category sits inside. It has a natural enlargement, which is the category of pro-étale local systems, or pro-étale vector bundles. So there's a pro-étale site. It has a structure sheaf. And the construction is simply you take L and you tensor over C with the structure sheaf. So this is very similar to what you would do with the complex numbers if you wanted to go from Betty to de Rham. In Faltings' work, this was called generalized local systems. You can model objects locally rather concretely, but let me not try to do that right now. And so the goal from now on is to sort of forget about this category and just talk about this category. In particular, I am not going to be able to tell you anything interesting about which Higgs bundles or twisted Higgs bundles are going to correspond to honest local systems. That's a very interesting question, and I don't have much to say about that. But I do want to describe this category over here in terms of Higgs bundles. And so the theorem is the following, and it's extremely analogous to the previous Kersig P story. So there exists a natural étale GM gerbe P over the cotangent bundle of X. Like before, except the cotangent bundle in p-adic Hodge theory always naturally comes with a Tate twist of -1. So it should always be there. And if I forget about it, it's because I forgot about it, not because I omitted it on purpose. So there's a natural GM gerbe like so, plus an equivalent like we had on the previous page. So I'll call the equivalence S. It goes from vector bundles on the pro-étale side or generalized local systems to exactly what I was calling p-twisted Higgs bundles on X. And so let me just remind you what this was. This was those coherent sheaves on P, which have degree 1 and the support conditions. So support of E is finite over X, and E is locally free over X. So again, if there was no twist, this would just be usual Higgs bundles, but there is a twist. So this is the statement, and I want to spend the rest of the talk sort of unwinding this. I'll make some remarks about it, and I'll try to explain how you can extract more concrete consequences out of it. Okay, so the picture for what's going on over here is the same as what was going on in Kersig P. So just keep this in mind. So let me first make just two simple remarks. related to things that were already happening in characteristic P. So the first is that, again, like in characteristic P, the gerbe is non-trivial. So if you look at the class of P in the Brouwer group, P star X, or I really shouldn't say Brouwer group because it's H2GM. It's the more, I mean, it doesn't have finite order, as it turns out. Is non-trivial, as long as you're not dealing with the trivial case. And in fact, has infinite order, as I was saying. So because it has infinite order, the situation is sort of different from what happens in characteristic P in the sense that you cannot write down a finite dimensional Azumaya algebra representative for this Brouwer class. The order has to be, if you had a finite dimensional representative for the Brouwer class, then the order has to be finite, which is not. I can discuss this more later, but let me just say this much for now. Okay, no, I want to say one more thing about it. So one way to sort of think about what's going on is that this is a p-adic lift of the characteristic P story. In particular, you can, if you're in a good reduction setting, you can specialize this p-adic gerbe P over here to what was happening in characteristic P in the first part of the talk. And therefore, since the specialization is non-trivial, you know that this one is non-trivial. But that would only tell you that it has non-zero order. It wouldn't tell you it has infinite order. In this case, it actually has infinite order.
Could you remind us what the -1 means?
-1. Oh, it's a Tate twist. So it just means that if you want to do things in a Galois equivariant fashion, the vector bundle of this question is not the cotangent bundle, but the cotangent bundle twisted by the -1 cyclotomic character. If you were just working over an algebraically closed field, for example, you can just ignore this. Is that okay?
Thank you.
Mm-hmm. And the second remark is related to the question that came up about symmetric monoidal structures. And so let me write it now. So this gerbe P is multiplicative. And so what this means is that if you think about the classifying map for this gerbe, I'm going to write it like so. So for each point of the cotangent bundle, you're supposed to produce a GM gerbe. And so you can think of it as a map from the cotangent bundle into the classifying space of GM gerbes, which is B squared GM. And the statement is that this is an E infinity map. So it's compatible with the group structures on both sides in the best possible way. And so concretely, what this implies is that P has a group structure. Lifting the standard one on the cotangent bundle. And which in turn implies, as I was saying before, that this category of twisted Higgs bundles is naturally symmetric monoidal. And then if you know this, then the statement is also that the equivalence in the theorem is symmetric monoidal. So, and S is a tensor equivalence. Okay, so this is really a symmetric monoidal equivalence. In particular, on this side, you have an interesting object, which is the unit object, just the trivial vector bundle. And so that corresponds to some twisted sheaf, to some Higgs bundle, or equivalently a sheaf on this gerbe. And usually it is non-trivial to write down degree 1 sheaves on GM gerbes, because that means that on the locus where the sheaf lives, you have trivialized the gerbe. And so what's going on in this example is the following. So, example. If you apply this Simpson functor to the trivial vector bundle O hat, what you get is the structure sheaf of the zero section. And oops, that didn't fit. And note that this makes sense because of 1, yeah? 1 says, sorry, because of just this fact over here. Since this is a group map, it's canonically trivial on the 0 section. And since it's canonically trivial on the 0 section, you can ignore the twist, and therefore the structure sheaf of the 0 section can be regarded as a twisted sheaf. And so the statement makes sense precisely because this gerbe was multiplicative. Okay, and then I guess the third remark is that there is a version of this theorem for perfect complexes, which I won't spell out. But it's useful because in particular, it tells you that this equivalence is compatible with cohomology. So Higgs cohomology corresponds to pro-Étale cohomology. Okay, so that's the statement of the theorem and some easy remarks on the gerbe. I want to next tell you about how you could extract some more honest consequences or more honest correspondences out of this statement. Are there questions before I do that?
Yeah. Yeah. In the characteristic P case, you have your equivalence is from D module. But here, I mean, D modules is like a presentable category. I mean, do you have, embed these, vector bundles, whatever, to an equivalence of presentable categories?
Yeah, so that's a good question. Let me just reformulate the question because maybe not everyone knows what presentable categories. You can ask if there's a version of this theorem which sort of allows things like constructible sheaves rather than just local systems. So something where you can, you have arbitrary cones and so on. You also have things supported on closed sets like in D modules. And I'm optimistic that there is such a statement, but I am not prepared yet to formulate a precise statement. So I expect there's at least a functor from Zariski constructible sheaves on the variety to twisted coherent sheaves on this gerbe. But that's all I've done so far.
So sorry. I mean, this is still not presentable, I guess.
Right. Okay. Those are the versions for finite objects, and then I guess you get a. I don't know the answer to your question in the form of an equivalence between presentable categories. I'm saying that there's potentially a functor between presentable categories which restricts to this equivalence on nice objects.
Okay.
Mm-hmm. Other questions?
Yes. What was the base? It's a rigid analytic variety, so there is no Galois. Because I'm wondering what it does on cohomology, your equivalence of categories.
Right. So on cohomology, let me maybe just write over here what it means. So for all E in X for all vector bundles on the pro-Étale site, what you get is the pro-Étale cohomology of the vector bundle is, if you go through what this says, it's that it will be R harms on this gerbe P from the structure sheaf of the 0 section into the image of E under the functor. And so if there was no twist, you could resolve the structure sheaf of the 0 section using Koszul resolution, and that would give you a sort of Higgs complex that computes the Higgs cohomology. And this is the twisted version of it.
Okay.
Is that okay?
Yeah, yes, thank you very much. Yeah.
No, thank you. Yeah. Okay, so let's try to extract some honest consequences out of this. Untwisted honest consequences. So the setup is the same as before. Let me just rewrite it. So X over C is smooth, C is perfectoid, and P is my gerbe. So I want to now tell you about what are the loci inside the cotangent bundle where you could trivialize the gerbe and get a true statement, untwisted statement. So the first one I want to tell you is the nilpotent case, like in Ogus Vologodsky. And so for this, again, so Ogus Vologodsky needed the choice of a lift to Z mod P squared. There's an analogous choice one can make here. So say X is lifted to something I'll call mat BVX over this ring that's sort of the analog of the Witt vectors in this setting, B2C, which is B to Rham plus of C, Fontaine's B to Rham plus mod T squared. So this is a square zero thickening of C. And let's assume you have such a lift. This is actually a pretty mild assumption, much milder than in P. If X was smooth and proper, such a lift always exists. But it's still a non-trivial choice. So let's make the choice. And so once you make the choice, then you have a reduction of structure group of the gerbe from GM to roots of unity. And so what this means is that we recall that we have this classifying map for the gerbe, P, which is going to P squared GM. B squared GM receives a map from B squared mu P infinity. And I'm saying that there is a factorization like this, where this factorization depends on my lift. But why is this useful? Well, first, it tells you a few things about the gerbe, which is the Brar class in question is really coming from a class with coefficients in mu P infinity, which means that on any quasi-compact open subset of the cotangent bundle, the Brar class actually has finite order, because on a quasi-compact open, it will actually come from mu P to the n, and so it'll have some finite order, that n. It's only that the orders cannot be chosen uniformly. So the cotangent bundle is infinite, is not quasi-compact. And as you sort of go off towards infinity, the orders keep growing. That's one thing that tells you about the gerbe. But more interestingly, since we're working in Kirsig 0, this group scheme is a tau. It's a discrete group. If you had roots of unity, it would just be a constant group, QP mod ZP. And what that buys you is that the gerbe, this map over here, since it was trivial on the zero section, it will also have to be trivial on any infinitesimal neighborhood of it. And so in fact, it trivializes over the formal neighborhood. So it's trivialized over the formal completion along the zero section, and the trivialization depends on the choice of the lift, because this factorization depends on the choice of the lift. What does that tell you? It tells you that if you only care about those Higgs bundles that are supported on this infinitesimal neighborhood, on the formal neighborhood of the zero section, then you can ignore the twist. Being supported on the formal neighborhood means exactly that the Higgs field is nilpotent. And so what this tells you is the following corollary, which is if you only care about nilpotent Higgs bundles, then you can identify them with the corresponding twisted ones, just because the twist is trivial. And this, in turn, by the theorem, was vector bundles on the pro-Étale side with the same nilpotence condition after you apply the functor. And so there is an intrinsic description of what nilpotence means on the pro-Étale vector bundle side, which I don't want to give right now. It depends on this canonical Higgs field on pro-Étale vector bundles that was discovered by Louis Penn and Juan Esteban Rodriguez Camargo. Again, things coming from geometry have a nilpotent Higgs field. And so for things with a nilpotent Higgs field, you have this kind of canonical equivalence. Another consequence of this is the following, which is this map over here, since it's trivial on the formal neighborhood of the zero section on the left-hand side, it's not so hard to see that the scaling action of GM on T star X is compatible with that trivialization, at least if you restrict to a small enough neighborhood inside GM. So more precisely, there is a natural GM hat action on P, lifting scalar multiplication on the tangent bundle. So the scaling action of on the cotangent bundle amounts to just rescaling the Higgs field by a scalar. This was exploited beautifully by Simpson to prove many wonderful things about representations. in the complex story. In the p-adic story, you don't quite have a full GM action, but you have sort of the infinitesimal version of it acting, GM hat. And again, this finding this action depends on everything in part one depends on this lift that I've picked. But you can use this, for example, to recover a result of Liu and Zhu that attaches nilpotent Higgs bundles to local systems which have an arithmetic structure. So you get nilpotent Higgs bundles for arithmetic local systems, meaning the local system and the variety are both defined over a discretely valued field.
But you don't say it's equivalent, or did you say it's equivalent?
I don't say what is equivalent. Sorry.
That arithmetic local system correspond to nilpotent Higgs bundle. You don't say that.
I definitely don't say that. No.
Thank you.
Yeah. No, all I'm saying over here is that this GM hat is some version of the Galois group acting. And if you think about, like, the picture of the cotangent bundle, here's the zero section. The GM hat is sort of scaling in the fiber direction. And for these local systems that come from arithmetic, they're going to be GM hat equivariant. So their supports have to be subsets of the cotangent fiber, which are stable under GM hat, which forces them to be near the zero section. That's all I was saying.
And I asked about the previous corollary. I think I asked you already. Do you have a description of the ones which are not only nilpotent, but also zero?
So nilpotent, if the Higgs field is actually nilpotent, that means it's just a vector bundle. So in this cotangent bundle picture, the nilpotent Higgs fields are the ones that are scheme theoretically supported on the zero section.
That is very good. It's fine. Thank you very much. But in the previous corollary, you define vector bundles on the proetal side, lower nilpotent at the inverse image via the correspondence. Then you say there is an intrinsic definition. And I ask about this intrinsic definition when you don't only assume nilpotent.
Sorry, that just means it's an actual vector bundle on X pulled back to the proetal side.
Just that. Okay.
Yeah.
Okay. Okay, thank you very much.
Mm-hmm. Right. So I should have said something which is like, I wasn't trying to claim originality here. So I think this nilpotent correspondence has been worked out by a lot of people. I learned from Ben that one of the original references was Suji. And there was a paper on the archive quite recently by a master's student from Bonn, whose name I wrote down. Okay, yeah, Tiago Neri. And here it was Liu Zhu. So I'm just trying to explain how these existing theorems fit into the story.
Okay, thank you.
Mm-hmm.
Sorry. Yes. There's an understanding of what happens if you choose different lifts. Do you really get different equivalences then, or?
Yes, I believe so. I think you would be twisting by something related to the Faltings extension. Sorry, I don't have it in my head, but I think if you use different lifts, you would get a different equivalence.
But this equivalence extend to the overconvergent neighborhood?
I don't know what that means, but yes. Right. So my understanding is that if I was more competent, I would probably replace hats with daggers everywhere in this talk, but then I would definitely not know what I'm talking about. So let me avoid doing that. Okay. So let me now talk about another specialization of this. So this is the global case. So this is the work of Faltings and Hoyer. So for this, I have to assume that C is algebraically closed. X over C is smooth and proper. and x is a lift to this square zero thickening that I mentioned before. So, well, you need some more choices, but let me just formulate it as follows. So this is due to faultings in dimension 1 and Hoyer in general from 20 years ago and 1 year ago, respectively. And so from the perspective that I'm explaining in this talk, the theorem can be written as follows. So P, this gerbe, trivializes compatibly on all spectral varieties. So let me say what that means. So the support of a Higgs bundle is some closed subset of the cotangent bundle, which is finite over the base. You can look at the union of all such subsets. So let's look at the union over all Z of Z inside T star X minus 1, Z finite over X. And the statement is, if you think about this as sitting inside T star X minus 1, this gerbe P trivializes over this locus. And so concretely, what this buys you is that every time you see a twisted Higgs bundle, you look at its support. The support is one of these Z's. You use your trivialization to get rid of the twist, so you get an honest Higgs bundle. And so using this trivialization, you get a equivalence between untwisted Higgs bundles and pro-Ital vector bundles in the setup. So you just forgot about the twist completely. The caveat is it depends on choices. So I mentioned some choices, which is that you have this lift to beta Rham mod t squared. You also need the choice of an exponential function for C. And my understanding is that you need some more base point data. And so one practical consequence of this is that this equivalence is not equivalence of functors. It's not compatible with pullback, which makes it a little tricky to use for me, but it's an extremely clean statement. And so this is just me reformulating what they did in terms of this gerbe, not doing anything new. Yeah, maybe one thing I should have said is, right, this subset over here is really a group. If you have two spectral varieties and you add them, you get another spectral variety. And so this trivialization can be chosen compatible with the group structure, which means that this equivalence will actually be a tensor equivalence. Okay, and then the third thing I wanted to say, which is much more work in progress than the rest of this talk, is a moduli version. And so this is building on so Hoyer and Shu in dimension 1, but also in characteristic P, I learned this from the thesis of Groshnig. Or, sorry, I don't know if it was a thesis, but an early paper he wrote in dimension 1 or in characteristic P. And it's the following statement. So let's say X over C is smooth and proper, but I don't sort of make any of the other assumptions I was making previously. So then you can contemplate the stack M Dolbeau of Higgs bundles. You can also contemplate this twisted version. I mean, I have this Brouwer class P, so I can twist everything by it. This is the stack of twisted Higgs bundles. Which by the main theorem is the same as the stack of pro-Ital vector bundles, at least pointwise. Both of these stacks have maps to the same base, which is called the Hitchin base. This was explained in one of Simpson's early papers in this topic for the left-hand side, and the same construction works for the right-hand side. Let me call them pi and pi p. Essentially, so okay, what is the Hitchin base? It's the direct sum from I equals 1 to the rank. I guess I should fix a rank for the bundle to make this statement, but let me. allow me to not decorate that further.
Bhargav, it was also explained in Hitchens' paper, you know?
Okay. I know you said that in your paper. I didn't do my job and look further. Thank you. So this is the map is essentially extracting the characteristic polynomial of the Higgs field. It's sort of easiest to understand in the case of dimension 1, where a Higgs bundle is just a vector bundle together with a map from the vector bundle to itself twisted by a line bundle. If you trivialize a line bundle, it's an endomorphism of a vector bundle, so it has some characteristic polynomial, and you record the coefficients of the characteristic polynomial. And you do the same on the other side using the intrinsic Higgs field. And the theorem that we expect to prove, meaning I've almost checked all the details, but not all the details, is pi and pi p are étal locally equivalent to each other. So there are twisted forms, étal twisted forms over the Hitchin base of each other. In fact, there should really be a better statement, which is why I'm hedging a little bit in writing this, involving a torsor for a certain group, which was so that version of the statement in characteristic P was explained by Chen and Zhu, building on work of Bezrukavnikov and Rham. But we haven't gotten that far yet, so let me just write it this way. And so the one interesting comment I want to make about this is, so I did not make any assumptions on dimension over here. So you could ask if the same story also works in characteristic P with D modules and Higgs bundles. And in fact, it doesn't. So, so the analog in char P fails, or at least as formulated, fails in dimension bigger than 1. And the essential difficulty is, or the main difference that makes it work better in characteristic 0 and not in characteristic P is that the group scheme mu P infinity is étal in characteristic 0, but not in characteristic P. So I'm happy to sort of explain this further if someone's interested, but that's essentially the point, that since the group scheme is étal, if you have a trivialization on some set, you automatically get a trivialization on a formal neighborhood of that set in characteristic 0, and that's the step that fails in characteristic P. And because of that observation, this theorem is essentially formal in the sense that it's not something specific about Higgs bundle or twisted Higgs bundles or pro-étal vector bundles. Whenever you have a GM gerbe on the cotangent bundle, you can ask whether or not the corresponding stacks will be étal locally equivalent. And the only input that you need is that the GM gerbe trivializes on all of these spectral varieties, which is coming from Hoyer's theorem. Okay, any questions about this?
Yes, I have a question. It's possible to define the stable part and semi-stable parts in this situation?
Maybe, but I haven't thought about it.
Okay.
Does that give an intuition what would be true in higher dimension, but over FP?
Yeah, I was wondering about that.
I think Gobao Zhao had tried to generalize Michel's PhD thesis in dimension 2, but he failed.
Right, and my impression was it was exactly this kind of Brouwer obstruction that that sort of, well, that's the first problem you run into. So yeah, we could talk about it, but I don't have anything interesting to say. So let me not do it right now. So I have about 7 or 8 minutes left, and I wanted to give you a construction of the gerbe. And I want to do this because, well, first of all, for completeness, but also because I think it illustrates really what is making everything work. And hopefully it also connects with Peter's talk, but I did not see Peter's talk, so my part. So C is perfectoid. X over C is smooth. And the question I would like to address is, how do you construct this gerbe? So there are two constructions I can give. Let me do the first one is easy, but maybe less illuminating, but let me just write it. It's more tautological. So essentially, the gerbe P is the Picard stack of the pro-étal side over the étal side. I mean, you're trying to define a functor that attaches étal objects to pro-étal objects. So there's some obvious Fourier-Mukai intuition that suggests that this is the right thing to look at, and it seems to work. And so concretely, what this means is that you have this push forward nu from the pro-étal side to the étal side. You push forward the units. Now that has the information of all the higher cohomology. You only care about pic. So you truncate in degrees less than or equal to 1. And then you shift it by 1 to make it a connective object. And this is a slight lie, but this is essentially what the gerbe is. And the non-triviality of the gerbe has to do with the fact that this complex, which has only 2 non-zero cohomology groups, is not split. There's an interesting X2 class there, and that's exactly the class of this gerbe. So if you like, it's a multiplicative version of what happens with Deligny-Loci. And that actually led to the following, which I find more understandable description of the gerbe. So this is via essentially Deligny-Loci in this setting. So the key idea is to use the sheaf OX plus inside OX. So this is the sheaf of bounded functions on the étal side. A sheaf of functions bounded by 1, really. And OX is the sheaf of all functions. This is an integral sheaf, unlike OX. OX is a rational sheaf, but OX plus is an integral object. And you can play some games with it, which are rather fun. And so let me tell you 2 interesting facts about this. So observations. So the first observation is that you could play the Deligny-Loci game in this setting, which is maybe not surprising. So the obstruction to lifting this map of rings from OC to OX plus across the square zero thickening, which is given by Fontaine's thickening. So A inf of OC mod D squared mapping to A inf of OC mod D, which is just OC. So this is a canonical square zero thickening of any perfectoid ring that was discovered by Fontaine. And you can ask whether this sheaf of algebras over this ring has a canonical lift, or has a lift to this thickening. It typically does not, and the obstruction to lifting is a map. So it's usually an element in X2, but let me think of it as a map. So is a map from the cotangent complex of OX plus over OC towards the ideal of the thickening, which is OX plus twisted by 1. And then there's a shift by 2 corresponding to the fact that we should be looking at H2 classes. Obstructions live in H2. So this is a very standard observation in deformation theory, but let's make it in this context. And then the second observation is, okay, so why is this useful? It's useful because the sheaf is a really funny sheaf. In particular, this complex is a really funny complex. So it looks like it's an integral object because it's defined using integral sheaves, but actually it's a rational object. So the cotangent complex of OX plus over OC is uniquely p-divisible. And so what this means is that it equals its rationalization, which is the cotangent complex of X over C. But that's just the usual sheaf of Kähler differentials because I'm assuming smoothness. So what makes this observation work is essentially the fact that étal locally on the generic fiber, you can extract lots of p-th roots of functions, and when you do that, differential forms become divisible by p. So the local rings of this of OX plus have sort of all differential forms being uniquely p-divisible, and that gives you this theorem. or this observation. And so why is this useful for us? It's useful because over here we have a map like so. So the left-hand side is a rational vector space. The right-hand side is an integral object. Whenever you have such a map, you can uniquely divide it by any power of p that you want. So let's do it. So 1 plus 2 imply that for all integers n bigger than or equal to 0, you get a unique factorization of the obstruction map in terms of sort of divided obstruction maps. So here's omega 1 of x over c, which I said earlier was ox plus over oc. I have this obstruction map, which goes to this integral object, ox1 twisted by 2. Inside here, I have its p to the n power subsheaf, which is just another copy of itself. And I get a unique factorization like so. Let me call this map op n. This is just because by some silly adjunction, because the left-hand side is uniquely p-divisible. But why is this useful? It's useful because once you have something that goes into an integral object and its image is divisible by a big power of p, you can exponentiate it. And so here's a definition. So let me just write the definition and then I'll answer any question. So you look at omega 1 of x over c. You look at this op 2. So take n equals 2. P squared ox plus. And let me move the twist over to the other side to make it a twist by -1. And then I can exponentiate because my entries are divisible by p squared. So the exponential makes sense. And it goes into gm, or ox star. And so this over here is the classifying map for the Simpson gerbe. So long story short, the obstruction map coming from Toulouse has extra divisibility properties, and you can exploit those to define the Simpson gerbe. And the last thing I want to say, which is the expected relation with Peter's talk, hopefully, is so you expect that so here I took this map and just used the n equals 2 version of it, and then exponentiated on the target. But I can also, since these are unique, I can also take the inverse limit of these. So the expectation is that the inverse limit over n of ob n classifies the analytic Hodge state stack. But if Peter's there, maybe he can confirm it. And if not, that is the last thing I want to say. So let me stop here. Thank you.
Well, thank you. Any questions?
I have a question. Yeah, so you said that that you take a local system and then pull it back to the pro-Hall site. That looks like sort of taking a local system and tensoring it with the structure sheaf. But wouldn't that thing have some kind of connection on it or something like that?
Right. So the structure sheaf on the pro-Hall side is locally perfectoid, and so the structure sheaf has no differential forms on it. Because of this kind of unique p-divisibility, you killed all the differential forms if you work pro-Hall locally. So it sort of has a different flavor for that reason.
Nothing that says that sort of locally functions aren't not necessarily locally constant or something.
Functions are definitely not locally constant here. Sorry,
the thing that says that they're not locally constant. The measures how not locally constant they are.
I mean, Bhargav, there you were implicitly p-adically completing.
Yes.
Right?
Correct, right. Right, so if you didn't p-adically complete, I think you would discover what's currently on the screen, more or less. Like if you... Sorry, I don't know how to answer that question. Like which sheaf do you want to use on the pro-Hall side? Like if you use OX plus, then it's basically the same as working with the Hall side. And then I think you end up running into what's currently on the screen. And if you use OX hat, then there are no differential forms. But
no, it's a question. It's not a statement. It's a question. Wouldn't there be some extra structure that sort of? I mean, in the complex case, well, if you know, in the holomorphic case, if you tensor with OX, then you've got a bundle, you got a vector bundle, but it has a flat connection and so on.
Right. So there's a tautological answer to your question, which is on the pro-Ital side, you have this constant sheaf C, you have the map to O hat, and you can contemplate what is descent data along this map. I don't know the answer. Like, I don't know a good way to say what the descent data looks like,
Yes.
other than something tautological. Yeah.
So you said, of course, it's a old-fashioned question, and I apologize. So you say you would not address the question to recognize the actual local systems among all the Higgs bundles you are looking at via the correspondence, but do you have a suspicion what it could be? I mean, it has been really an interesting question for a time, launched by Pierre.
It's extremely interesting. I don't have anything to say about it beyond what others have already said about it. So my understanding is that maybe the expectation or the guess is if you work over CP, so not over some random big perfectoid field, but actually CP, then the answer should be as in Kirsig 0, which is Higgs bundles, semi-stable Higgs bundles with vanishing Chern classes. But I don't know if we're close to proving that.
But that would be, of course, very beautiful. But if you go beyond CP, it will not be true. That's your intuition, or you know that?
No. So I think Ben explained this nicely, which is if you go beyond CP, there are just some obstructions coming from line bundles. Like there are more invertible objects on the pro-Ital vector bundle side than on the local system side. So.
Okay.
Like somehow, I think the idea is that the local things coming from local systems should have some triviality mod p. But if you work over some big field where the residue field is not FP bar, but something which has a transcendental element, you might have degree 0 line bundles there, which are not torsion, and those would probably not correspond to local systems.
Okay.
No question.
Not sure whether it's.
Please. Oh, no, but someone.
I'm not sure whether it's naive, but is it direct to get August FP correspondence by mod P by your correspondence directly?
So we're not doing anything that you wouldn't like. Nothing we're doing in Kirsig 0 would be different from what we already do in Kirsig P. So I don't think it would be a new proof, but you could wonder if there's a common refinement of the two, which is if you have something in mixed characteristic, is there something that matches the Ogus Vologodsky correspondence mod P, and also the one I just explained over the generic fiber? And to this, the answer is yes, or at least over the formal completion of the 0 section of the cotangent bundle. So more precisely, okay, let me just very quickly write something. If I give you some smooth formal scheme X over OC, you can write down a gerbe over it's the formal completion of the 0 section of the cotangent bundle integrally. And this gerbe, if you reduce mod P, it specializes to the Ogus Vologodsky's gerbe. And if you invert P, it equals the gerbe you have on the generic fiber, but with a caveat. So the generic fiber of the integral cotangent bundle is like the radius less than 1 part of the cotangent bundle on the generic fiber. And so that's the only part you see this way. And there's this slightly annoying issue of the hat. It would ideally be better if you didn't have the hat. And we're discussing with Vologodsky, pretty sure the answer is yes, but there are some technicalities, and so we haven't quite sorted it out yet.
Yes, I think probably my question doesn't make sense, but the classical story of RFP is that the gerbe of what P square local lifting was in fact the class of certain cotangent complex of X with respect to CP. So here it's a different thing, and I don't see this orb as the class of some cotangent complex, which will be perfect and concentrated in degree -1 and 0. So
it is. It's exactly that. It's the cotangent complex of OX plus relative to A.
If you take the zero infinities one, the neighborhood be either on 2, you said, of C, then it's always split. So then it's not good. So
No. But this gerbe is an integral object, and integrally the analog of that statement is false. And so the statement I'm making is that this over here, this two-term complex, is the cotangent complex of OX plus over the constant sheaf A, suitably completed.
Can you say it again? It was too quick for me. Yes.
Wait, sorry, is my screen still sharing?
No, it's just you speak.
Can you say it again? Yes. This potential complex with potential complex.
Wait, let me just try to share my screen again, because I was writing on the screen and I'm trying to answer the question. For some reason, it takes a few seconds. Okay. Yeah, I assume people can see it now?
Yes.
Right, so this ob, which is the map you're asking about, is that two-term complex is the cotangent complex of OX plus over A. So there's some transitivity triangle.
So it's, the splitting corresponds to some lifting in some sense.
Splitting corresponds to lifting the sheaf to A mod T squared, but I think that basically never happens.
Yeah, sure. And then at the very beginning, you said that even if you started with something with the algebraic model of formal completion of something algebraic, then you need some analytic theory. So it comes maybe from the exponential at the end.
Right. So that's why that's why the construction wasn't working in pure algebra. But I mean, that's the construction, but also I'm saying in terms of the output, it had to be non-algebraic because this gerbe had infinite order. And so, yeah, it can't be. If it was algebraic, it would have finite order. Also, the gerbe was trivial along the zero section. If it was an algebraic gerbe, then homotopy invariance would tell you that it would have to be trivial everywhere, but it's very far from it. So the gerbe is definitely a very rigid analytic object.
But sometimes you approximate exponential by Coulomb extension. There's no such theory there.
I think that kind of question will come up in trying to get rid of this hat, and we're talking about it. Yeah.
Thank you.
Any further questions? Okay, how about this?
Thank you.
You have the wrong switch off, Bhargav. You have to take off with us.
I can see you now. I actually maximized your window so I can see you better than.
Can you see me?
Yes, hi, Luke.